Hello, Math 30-1. This particular unit that we're doing, functions and relations, is somewhat a review and gives some building blocks into some of the functions we've seen in the past and that we will use as we go through 30-1. So if we look at lesson 1 in particular, there's not a lot that you haven't seen before. Just maybe a little bit deeper and so on. So if you look at the definitions, and I'll just really quickly go through, if you look at a polynomial function, in x is a function in the form such that, as we see, these coefficients have to be real numbers, and we also know that these exponents up here, those need to be natural numbers or whole numbers. For example, this polynomial, we look, and in the one in particular, the highest degree is 4, and so it's a degree 4. Its leading coefficient is a 1 because the leading coefficient is the coefficient of the highest degree term, and the constant term is 5 because it has a 5 that has no variable on it at all. The common polynomial functions that we use for transformations are y equals x, y equals x squared, and y equals x cubed for cubic functions. A linear function is degree 1, and we talked about that a lot in Math 10. Another function that we've talked about a lot is something called a constant function, and in a constant function, a function whose value never changes. It's a polynomial function of degree 0 and can be written in the form y equals 3. And that is a horizontal line, but as we've seen in the past, we also have axes of symmetry and so on, where they are lines like x equals 3 and x equals 2. Okay. If we sketch each of the following, we can sketch a line where it has a slope of 3 and a y-intercept of 1. We can sketch a constant y equals 5. And we can state the domain and range for each of those, as you can see there. And if you need to slow down and pause it, you may. Right? But that one's kind of a boring function. If we carry on to quadratics, you can see that in quadratics, we have in general form ax squared plus bx plus c, where a can't be 0, and in standard form we have ax minus p squared plus q. We can use a graphing calculator to sketch the graph, and we can get zeros. We can see from that the coordinates of the vertex are 3/2 and minus 81/4. Your calculator is going to give you decimals, but just to remind you, there's also a really cool way to do it, and that is by doing something called completing the square. So I'm just reminding you of some 20-1. So if I complete the square, I get x squared minus 3x. And I divide the middle term by 2, so that gives me 3/2, and I square it, so that gives me plus 9 over 4, and also I add minus 9 over 4, and I still have the negative 18 from before. So when I complete the square, I've got x minus 3/2 squared, and when I put the minus 9/4 plus the 18, that's where I get the minus 81/4 that they have there. That's where the exact values, or you can use fractions. What's the domain and range? You can see there. If we use factoring to determine the x-intercepts, as you can see right there when it says zeros in question B, well, we let y equal 0, and then we get a quadratic, which then we factor and get these factors, which therefore we use that 0 theorem and say that x equals 6 and x equals negative 3. Rewrite the equation in standard form. Explain how this helps determine the coordinates of the vertex. That's what we just did up here, and that's how you kind of get to it in that really quick little explanation I gave there. If I use a graphing calculator to determine the zeros for especially a graph that this one obviously does not have nice integral zeros. Here in this case, we put them to the nearest hundredth, and that's using the 0 function of the calculator, and you have to do the left bound, right bound. The quadratic formula is much more powerful because it gives exact values, and with that, we can now see that they're clearly minus 2 plus or minus the square root of 7 over minus 3. And that is the only way to get the exact values, right? When we look at example 4, in example 4, it talks about a cubic function, and if we use the graphing calculator to sketch it, we can see there that we've sketched that. If we use the feature of the calculator to determine the x-intercepts, we find, and I think this thing moved a little bit, we find that the x-intercepts on the calculator are minus 0.8, 2.0, and 5.2. The absolute value function, as you can see there, that's a really important one for calculus and so on. It's a special little function. It's really what they consider something called a piecewise function, because the absolute value of x, if you are considering positive values of x, is really just y equals x. But if you're considering negative values of x, then you have a function of y equals minus x. And that's where we get these two different functions. In this side, in the left side, we've got y equals minus x. And on the right side, you've got y equals positive x. And they together make or build the whole function called y equals absolute value x. But it's really a piecewise function made up of half of a line of y equals x and half of a line of y equals minus x. Sketch and graph the absolute value function of y equals absolute value of x minus 2. And in that's a function where the absolute value of x, and we talked in our transformation unit, it's an absolute value function that has shifted 2 to the right. But if you graph on your calculator, you'll see, and the domain is x is real numbers and y is greater than or equal to 0. A radical function is something else that's a little bit special. And a radical function, you can't take the square root of things that are negative. And so therefore you have restricted domains. Domain is x such that x is greater than or equal to a half, because a half makes it 0. And the range is y such y is greater than or equal to 0. It really ends up being half of a parabola, and it has a starting point at a half. So there is your starting point of a half, and then it's this, and that is the graph of y equals positive square root of 2x minus 1. On the next page, it talks about functional notation, and this really is review. You did quite a bit of work with this, but it's so important when we talk about substitutions and so on and transformations. And so when you plug in f at 2, just plug in 2. But variable substitutions, and in the transformations unit, it's really important when you are transforming a function. If I make a substitution of 2x, what does that do? Well, we know in transformation, we're not supposed to know it yet, that will cause a horizontal stretch by a factor of a half, whereas 2 on the outside will cause a vertical stretch by a factor of 2, and so on. So what does it look like when you do each of these things? Have a look and see if the answers there make sense, and you can pause and give those a try. Considering the function f at x equals x cubed, match each of those. And how do you transform x cubed so that you end up with each of those expressions? Well, clearly, obviously, x cubed becomes this, and x plus 3, and so on. So I want you to give that a try and see if that makes sense. And lastly, question number 9, f at x equals absolute value x. Write the following in terms of f. How do you take this starting input and transform it into each of these? What did you do to f at x? And this again is a lead-in or a reminder of how we do transformations with functions and what we do to those things. Okay, so have a look at that, and please give those a try and talk to Mr. K if that doesn't make sense. Well done.